Okay, so that steam chest, keep this end, left hand end at 100 degrees Celsius. The rod is long because we want it to be large temperature gradient between these two. Because we want the temperature not to be temperature as far as possible. You want to keep it one high, one low, so that the percentage uncertainty will be smaller. And then we make this length also large to reduce the percentage uncertainty. And then this end is just apparatus, is just to measure the rate of heat flowing in the rod, that's all. So lagging to prevent heat loss or to reduce the heat loss. And then we measure the mass collected in time t. Right, steady state. Steady state means the temperature doesn't change anymore. We just look at the temperature. Then we look at it a little while later. If the temperature doesn't change, then we have reached steady state. And we use the formula. Right? C is the specific capacity of the rod. K is P over AG. M is the mass of water collected in time t. So we can calculate our P, dq dt. Right? That is your SPM work. MC, difference in temperature, T3 and T4, divided by the time. That's the time. And we can calculate this P. Area, we can measure the diameter. Right? We don't want it too thin uncertainty in diameter, so it's thick. That's why we reduce the uncertainty. And you can calculate your temperature gradient G, T1 minus T2 divided by L. Material used is in the form of a, so if it's back conductor, is slightly different. Right? Material used is in the form of a thin disc with large diameter. The third point in your page 289. Why we do that? When the disc is thin, heat loss on the side are negligible. Right? Because it's thin, very little heat is lost, and then diameter is large, so heat loss from the side is very small. A lot of heat is flowing through the area. As the surface area of the side is negligible as compared to the cross-sectional area. Right? That's why we use large diameter. For conductor, we have another problem. We have to use the thin disc, because if it's long, it takes a very long time for the heat to flow through. But if it's thin, then okay, it doesn't take much time to reach steady state. Okay. That one, the rest I can leave it for you to read up in your note there. Your notebook, your book there tend to use thermal resistant, but I don't think you need to know that because unless they want to use your SPM work. Anyway, the same idea. Now, that is your conductor. There's your battery, if you like. There's a conductor. The current is flowing. I is the current. And V is the potential difference. This is a potential difference. So R is the resistance. So our R is just a potential difference divided by current. So if it is a conductor of heat, same thing, we lack it. But the current flowing in this case is the P. P is the one that's flowing, rate of flow of heat energy. And then instead of V, potential difference, we have your delta theta, temperature difference between the two ends. Delta theta, length is still the same. Length is the same. So we define our thermal resistance. Thermal resistance, RT, is delta theta over P. Then calculate our, use the formula there. Formula.
Wait, this is like derivation or something like and substitution.
So it's just to relate to you that there is an equivalent between electricity and thermal conductivity. That's all. Which I don't think they will ask you, because resistance is next semester's work. But they can still ask you, because it's more like SPM. That's all. You need to know how to compare. Okay, so we have a thermal resistance. V, we call it temperature. Instead of potential difference, we call it temperature difference. And the thing that's flowing in electricity is current. Thing that's flowing in this case is P. And then from there, this is your P. Right? Put in your value, equals to, right? Take it across there. Dx is your L. Right? You want to find this one. D theta over Ka. Take the Ka down. Right? This is your P. This is your P. That's your P. P. Take the P down. There's your d theta, dt. D theta, and then there's your P. You take it down. And you take your dx across there. Dx is your L. Ka, you take it down. Don't bother about negative sign there. So it's quite similar to our resistance formula, except this is resistivity. So it is conductivity will be at the bottom there. Right? So same formula, almost the same. Okay. We call K. K is our conductivity, not our resistivity. Okay with that?
Okay, Chen.
Okay, so we have completed. You can try the question at home. Conduction in conductors by free electron, in insulator by vibration of particle. That conductor also got vibration of particles or the ions, but free electron is faster. Insulator, the vibration is very slow process. And that's the formula. So you need to memorize what is P, what is a unit for conductivity, what is A, cross-section area, and what is temperature gradient, or whichever formula you prefer. Right? I prefer this one, easier to remember. Make fun of the formula. Right? This part is for lagging. This the graph is unlagged. And then T0 is the surrounding temperature. Right? And then you can, that is the gradient. Gradient give you your P over Ka, right? Or inversely proportional to your thermal conductivity. And then you need to know that's what we have gone through the graph. Right? That Kx is greater than Ky. This is less steep and steeper. Okay, let's go to 11.2 convection. Page 309. Convection, what is it? It's the transfer of heat by hot material carrying heat with it. That's your number one. It occurs in fluid or in liquid and gas. Example, you heat a pot of water over a flame. That's your flame. That's a pot of water. Right? At the bottom there, where it's heat up, the volume expand, volume of water expand. Right? The density increases. So it's less dense. You move up. Cold water start moving down. So that's your convectional current. Hot one goes up, lighter. Cold one, heavier, will move down. Then we have natural and forced convection. Number 4 and 5 in your note. This is called natural. Nothing there. You just let the normal air flow to it, so that it will lose heat. Convection current are set up by gravity. Cold fluid is of higher density, so it sinks. That's natural convection. Forced convection, we have a fan, blow the air to cool the cup of water. Movement of fluid is caused by external force, the fan. Example, a fan blowing over the hot object.
Yeah, it means it's a forced convection.
Force, we force the air to move lah. Newton's law of cooling, number 7, rate of Heat loss to surrounding is directly proportional to excess temperature for forced convection. What's excess temperature? Well, you have a hot body. This is a hot body with temperature theta. Right? Room temperature or surrounding temperature theta I. So we just write down Newton's law. Right? That is your rate of heat loss. There's your constant there. And excess temperature is theta minus theta I. Let's call excess temperature. Okay. Okay, it's just a constant. Okay with that?
Okay.
Right? What is forced convection? You force air across the body, blow air across the body to cause it to lose heat faster. What happens when the rate of heat gain is equal to heat loss? Yep. What happens when the rate of heat gain is equal to heat loss?
It's constant.
Temperature doesn't change anymore. Temperature stays.
Yeah, constant lah.
It doesn't gain heat, so temperature remains constant. It stops rising. Body temperature, the temperature of the body stop rising. Okay, convection current in atmosphere. That is what you have done in your SPM. You can just refer to your note there. Right? Land heats up and cools off faster than water because it has a lower specific heat capacity. Therefore, land gets warmer during the day. Land heats up faster. Water heats up slower. At night, it's the other way around. At night, the land cools faster. Right? In this case, during the day, it heats up faster. So the hot air, less dense, move up. And then the cold air from the sea or from the ocean move in. And the cold air start to come down. So there's a calculation. We got the sea breeze. During the night is different. During the night, the land is already cool. The sea is still warm. So in this case, the warm air will rise from the water, and then the breeze will blow from the land to the sea, because the land cool down faster during the night. Can SPM work? Okay, not okay.
Yeah, sea breeze and cold breeze, right?
Yeah. Daytime is the sea breeze. At night is the land. The wind is going out from the land to the sea. Okay, okay or not? All SPM work. So just review your SPM work. Nothing much.
Okay.
Then radiation is the transfer of thermal energy from a body to its surrounding in the form of electromagnetic radiation. That's your sun, hot body, earth, cold body. There's your electromagnetic radiation. The space, it can be vacuum. Radiation from the sun reaches the earth through vacuum. Right? Space is vacuum. All bodies emit radiation. Right? Your body, you are warm, it gives out radiation. Whether you heat it or not, doesn't matter. Our body give out radiation. Ours is in the infrared region. All body whose temperature is above 0 Kelvin. As long as it's above 0 Kelvin, it emits thermal radiation. Bodies at low temperature.
As long as it's above 0K.
As long as it's below 0 K. Bodies at
no, below 0K or above 0K?
As long as the body is above 0 K.
Okay.
Bodies at low temperature emits radiation of long wavelength in the form of infrared region. Bodies at higher temperature emit radiation in the visible and ultraviolet radiation. Okay, that's your SPM work. Right? Just review your electromagnetic radiation. Right? Longer wavelength is on this side, on the right. Shorter radiation is on the left. This one you study in the last semester lah. So when they say infrared wave, the one emitted by our body is this side, this region. Right? Longer wavelength, shorter wavelength of infrared is here. Right? Don't get confused. Infrared is not one wavelength. It got a region, a range of wavelength.
Yeah. Okay.
Okay. So the longer the wavelength, the smaller is the energy it carry. Right? If you can take this formula lah. This one you study, I think, the last semester. E energy of photon, energy of the wave, like you like. Right? We think of it as a particle lah, equals to HF. H is Planck constant, F is the frequency. So if the higher the frequency, the greater is the energy. That will help you. You can remember the formula. It won't be asked you like this is your third semester. And then your speed of light is equals to frequency times wavelength. And that means it's inversely proportional to wavelength. Longer wavelength, less energy for the wave. Okay with that?
Okay.
Okay, measuring radiation, number 5. Right? You have your conducting absorber. There's your incident light. You want to measure the radiation. And then this one is your dielectric material. And then this one taking the current out. You can measure the current and the voltage using you can bias it to measure the current and the voltage. Human skin is quite sensitive to thermal radiation. Right? We can feel whether it's hot or cold. Instruments are used to measure thermal radiation are mercury thermometer. All you need to do is blacken it. Blacken it so that it can absorb energy. Bolometer, thermopile. We look at bolometer. That's your barometer. That's your conducting. This part. There.
Che, can stop here, Che.
Okay. You stop here.
I mean, I can't absorb already. I think
No
I have to
problem.
read back everything. Then I ask you back is even easier, lah, Che.
Yeah, you got question to ask, you can ask, no problem. We can do a half
Because
an
you
hour.
reveal to me everything now, then later I might
Send
be
ready.
hard to explain, lah, Che.
Send
Yeah,
last week
send
already.
ready. I already got it ready.
Okay, so I'll stop here.
So I study that and then I ask you, lah,
You got
Che, easier.
question, you can tell me. We will spend half an hour to do the question.
Oh, or the notes also, right?
Notes I've sent you already.
No. If I have any doubts with the notes, like questions to ask.
We'll clarify with you.
Okay. Thank you, Che.
Okay.
Thank you. Bye-bye, Che.
Bye-bye.
Thank you.